lectures. So you'll be able to go back and rewatch any lecture if you like on CourseDen. I will also be posting PDFs of our whiteboard every day on CourseDen. So what I'm writing here on the screen, you'll be able to see.
I have a quick question, Professor.
Yes.
Um, do we have to be here for the lectures, like for attendance? Because I'm currently in San Diego and it's 5 in the morning.
Yeah.
Yeah.
Feel free to go back to bed and watch the lecture later. That sounds terrible. I'm sorry.
Okay. No, it's cool. I'm already up. I was just wondering. I like just kind of found the email last night. And I was like, uh-oh.
Oh yeah, yeah. No, I'm not going to be doing attendance anymore. Yeah, actually, this is a good time to talk about a few things. That's not the right sheet of paper. Where is my? There we go. Um, so obviously everything's different now. So we're not meeting in person anymore. We're meeting online, and hopefully, yes, I know my mic isn't on. It's not supposed to be on. As long as you're watching the lectures and hopefully showing up so you can ask questions, but if that's impossible due to your geographic location or something, I understand. I don't expect we're not going to have any hiccups. I don't expect everything's going to go 100% smoothly like it did before. I'm going to work with you. We're going to take one thing at a time. So today I just want to try to get the lectures working for everybody. As far as things like homework and tests go, I'm going to be reopening the homework. Right now, the homework schedule is wrong because we lost a week of class. As far as office hours, we've actually got a good deal there. Previously, I was only on the Carrollton campus twice a week, but now I am literally sitting in my bedroom teaching you, and so we can do office hours, weekdays, weekends, mornings, evenings, whatever works best. So I'll be sending out a doodle poll of all of the times I'm available, and you can just let me know when you'd like to have office hours, and then we'll meet in a CourseDen room just like this one. So since we lost 150 minutes of class time, I'm going to be recording some extra lectures on here, so that you still get all of the college algebra that you paid for. I want to make sure we do get through the whole curriculum, so you're fine for the next class in the sequence. If you have to take pre-calc or business calc, I want you to be prepared for that. But as far as grading goes, I'm going to be pretty lenient since we're all in such a weird situation. I know a bunch of people still have to make up old tests. If you've emailed me about that and I haven't gotten back to you, I apologize. I've been behind on email with this whole crazy transition to teaching at home. But I'll get caught up on that soon. And in the meantime, what we're going to do is the next test is going to be a take-home test. And that just means I'll send you the test, you send me a picture of your work, and hopefully that'll be fine for everyone. It means that you can take it kind of stress-free on your own time and just send me your best work so you're not stuck 75 minutes in a classroom with everyone. The final was going to be a department-wide multiple choice, and it still will be a department-wide multiple choice, but now you'll be taking that on CourseDen. So when the time comes, I'll show you how to log into CourseDen and take your test there, and I'll be here on this meeting room during the final to make sure no one has any trouble. Let's see. Does anyone have any questions for me about how the class is going to look from now on, or anything else? Oh, that's one other thing. If you do have a question at any point during today, do you see down at the bottom here we've got a little raise your hand icon? So I can raise my hand, you can raise your hand. What I found out yesterday is that CourseDen doesn't tell me when you raise your hand, but it does tell me when you lower your hand. So if you do need help or you're lost during the lecture, just double click that little button so you raise and lower your hand, and then I'll get a little chime and we can stop and answer questions. I know it's a little bit weird, but that's just how the software works for some reason. Did anyone have any questions?
No.
Okay. Well, what I'd like to do today then is get started on our fourth and final unit. So far we've learned about what functions are, and we've studied, excuse me, we've studied polynomials as a good example of functions. We just finished that unit before the break, and most of you have taken the test now. For those who haven't, we'll get that made up for you soon. We're going to be studying a new kind of function now. In Unit 4, it's called an exponential function. So this is a new way to talk about things that change over time. It's a new kind of change. What we already had was, I want to contrast this, I want to contrast this with linear functions. So I want to do a compare and contrast here. We've already seen what a linear function can do. That's any function that's a straight line, and so it represents, constant change, which is to say, maybe I'm measuring my cumulative sales from day to day, and maybe on day 1, day 2, day 3, I had a bunch of pre-orders. So let's say on day 1, I have 150 sold. On day 2, I have 200 sold. And on day 3, I have 250 items sold. So we can plot these points. This is a Cartesian plane, just like we're used to. Maybe this is the point 3, 250. So we're used to functions like this. And when I say constant change, what I mean is that if I go 1 day to the right, I'm going to go 50 days up. I apologize. There's a bit of lag on this whiteboard. So anytime I go 1 day to the right, we're going 50 days up, or 50 items up. So this is a constant change. No matter where we are on the graph, the change is always the same. The rate of change, we saw this, I believe, in Unit 2. The average rate of change and the instantaneous rate of change are the same here. They're both the slope. So I can say the slope here is 50 because when we have a run of 1, we have a rise of 50. To contrast that with exponential functions, these are, an example of proportional change. So in the linear function, it doesn't matter where we are on the graph, the change is the same everywhere. In an exponential function, the change is going to be proportional to whatever we've already got. A really easy example is a doubling function. When I say proportional, I mean, let's say we start with, you know how bacteria reproduce, right? If you've got a bacterium, let me draw one here. Here's the cell and the nucleus. Let's see if that'll update. There it goes. There's the cell and the nucleus, and it kind of elongates itself into a figure 8, and then that splits into 2 separate cells. So that's called mitosis. So if I have 1 bacterium, then maybe tomorrow I'll have 2. It'll have performed mitosis once and it'll split into 2. So I start at time 0 with 1 cell, and then I go to time 1 with 2 cells. But this is not going to be a linear function. It's not going to look like this. We're not going to go 3 and then 4 and then 5, because this is proportional change, once I have two cells, each of them is going to divide like so. Each of them is going to divide. So on day 2, since each of them split, now I'll have 4 cells. So the growth rate of this colony is proportional to the number that I already have. On day 3, I'll have 8 cells. So we've got a shape that's accelerating upward. And how we're doing it is every time we go 1 to the right, this rate of change does something new. It gets twice as big. So instead of multiplying by the same number over and over, instead of adding the same number over and over, we're multiplying by the same number over and over. That's the difference between linear change and proportional change. So this is the new kind of function that we're going to study. This is a geometric introduction, but I'm also going to do some real-world examples, and we'll talk about the algebra of them in some pretty great depth in the coming days. Does that make sense so far? Sounds like we're so far so good then. All right. Let's see. Oh, excuse me. When you saw me in class, I had already been awake for a few hours because I had to, get up, shower, get dressed, eat breakfast, drive to campus, review my notes. But now that I'm teaching from home, I can just kind of roll out of bed. So I haven't quite gotten all the yawns out of my system yet. My apologies. How is everybody doing, like emotionally right now? I just mean I want to, there's an example that I have in mind for exponential growth, but it's very much related to current events. So we can skip that if anyone feels uncomfortable. Otherwise,
No, I'm feeling pretty good.
Yeah, I am pretty unhappy with all these changes. I mean, I think you just got to find like a new hobby to keep you sane. That's what I've been doing. So far, I built a table and blazed a trail through the woods in my backyard. So I'm just trying to do whatever I can to keep myself busy. Cause yeah, this is super lame.
I'm running out of Netflix.
Netflix, yeah, me too. I just started Tiger King last night. Let's see. So, if it's okay, then the example I had in mind is that exponential functions are really good for describing how infectious diseases spread. So I don't know if you've seen. Where is it? That's not it. Here it is. Oh, I haven't looked at these yet today. I wonder how we're doing. Go on. There we go. So this graph right here, this is the number of COVID cases we've got in the United States every day. And it's got this long, you can see my cursor, right? Yeah, it's got this long, mostly flat part, and then it starts ramping up faster and faster. This is a perfect example of exponential growth. So when we talk about exponential growth, we're talking about, this is a very real world, what's my word? It's one of the most common kinds of change that happens in the real world. It's the archetype of a runaway process, like what we're seeing here. And here's how this works. Here's why this is the same as like this bacteria doubling function. They're all examples of the same kind of function. What's going on with COVID is, let's say maybe every day there's a 10% chance to transmit the illness to someone else, like each person who's sick has a 10% chance of transmitting it, then if there are if there are 100 people sick today, then 10 of them will transmit it and there will be 110 tomorrow. But if there are 1,000 people sick today, then 100 of them will transmit it and there will be 1,100 sick tomorrow. So the rate of change, we're not adding the same amount every time. It's proportional to these numbers. If there were 1 million people over here, there'd be a new 100,000 over here. So it's the same thing though, it's a multiplier every day. This time we're multiplying by, to go from here to here, we're multiplying by 1.10. So that's, go ahead and load there, please. This is the 1 represents all the people who already had it, and the 0.10 represents the 10% of new people who are going to get it. And so what you get is a process where however many people have it now, that number gets 10% bigger, and then 10% bigger, and then 10% bigger, and then 10% bigger. And that's how you get that curve that I had on the other slide. Now, eventually, one thing the exponential model can't predict is eventually we're going to run out of people and this will level off, but it could be some time until that happens. So until then, we're stuck here eating pasta. I started a vegetable garden the other day. I don't know about y'all, but we'll see if anything grows. Maybe a nicer example of the difference between linear growth and exponential growth is interest in a savings account. So linear growth would be, I don't know if you've ever seen these in a math class before. I know they're taught in a lot of places, but linear could be something like simple interest, and exponential growth would be compound interest. So if you've seen these before and you remember them, this might, let's say that we invest $1,000 in a savings account, and we're getting a really nice interest rate. Let's just make it 10%, so the numbers are easy. The way that simple interest works is we're just gonna, let's see, our interest, let me write year 0, 1, 2, and 3. So in year 0, we have $1,000. And the way simple interest works is the interest rate is 10%. And so we're going to get 10% of 1,000. So we will add 100. And then in year 1, we'll have $1,100. And in simple interest, it's really easy to keep computing. You're just adding the interest over and over. You're only making interest on what we call the principal. That's the amount that you originally invested, this $1,000 here. And so in year 2, we get another $100 interest check, and now we have $1,200 in our account, and then $1,300. Whereas the difference between that and compound interest is in compound interest, we say we start out with 1,000, and then we have 1,100. Whoops. So the reason I'm using my iPad notes here is Blackboard, the room we're in together, it comes with a whiteboard that I can share, but it doesn't have an eraser. I can't use a whiteboard without an eraser, so I'll be using iPad notes here. And then the really nice thing is I can make this whole thing, scroll all the way up to the top and back down to the bottom. I can use this whole thing as a PDF. So I'll be posting these PDFs of our whole whiteboard on CourseDen, never have to erase anything. So that should be really good for studying for you later. So in compound interest, what we say is, this it doesn't seem fair that we only get another $100 because we added 10% interest. That's the same as multiplying by 1.10. The one is for the money we already had. We keep that 1 times $1,000, and we add an extra 10%. We add an extra 0.10 of it, so we keep the 1,000 and we add 100. But in the second year, it feels like we shouldn't just be getting interest on the $1,000 we had before, because now we have 1,100 in the bank. We should get another 10% interest on all of that. So 10% of 1,100 is 110. So we're going to add 110 now instead of just adding 100. And so our balance is going to go up to 1,210. And then in the third year, we'll do the same thing. We'll multiply by 1.10 again. And so instead of adding 110, we're adding 121, because that's 10% of 1210. And now we're going to have 1331 in the bank. So in compound interest, you're making money based on what you already had. And so the actual rate of change, like the slope, the rise over run, that thing we computed in section 3.3, it's not going to be constant anymore. It's going 100 and then 110 and then 121, and then the next one will be $133.10 and so on. That's not constant anymore like it was over here, but instead the multiplier is the same every time. We're adding, 10% more, 10% more, 10% more. So this simple interest, if I graph this, we started with $1,000, and then we go up to 1,100, and then 1,200, and then 1,300. And this graph is a straight line, whereas the compound interest, we start with 1,000 and then 1,100, and now we're going to add 110. So this segment is a little bit steeper, and then we'll add 121, so it gets a little steeper again. And now we're only multiplying by 1.1 here, not 2. So the slope is a lot gentler than it was in the doubling function with the bacteria I had before. But in the end, what we do get is a curve that starts just slowly ramping up. It's accelerating upward. It's getting steeper and steeper the further you go. And this is an exponential function. So far, so good. Oh, someone's got a hot microphone. All right, so over here with the line, if I wanted to write a function for how much money we'll have so I don't have to keep adding 100 over and over forever, what I can do is I can write f of x equals, we started with 1,000, so that's our constant term, and then every year we're adding another 100. So however many years it's been, if it's been X years, go on, update. There we go. The whiteboard just gets stuck sometimes, and then I have to move my fingers on the screen until it unsticks. We have $1,000 to start with, and then 100 times the number of years, so $100 for every year. So if I wanted to know what I had in year 3, I would just write f of 3 equals 1,000 plus 100 times 3, and that's 1,300. And if I wanted to know what I had in year 10, I'd write 1,000 plus 100 times 10 is 2,000. So the function's algorithm here is a shortcut because I don't want to have to add 100 10 times in a table to get my answer. Now with an exponential function, we're going to do basically the same thing. Multiplication is repeated addition. So I used multiplication here to add 100 over and over. I added 3 100s or I added 10 100s. Here I'm repeating multiplication. So I need to do what's repeated multiplication. I'm going to say g of x, we're going to start with 1,000. And then every year we're going to multiply by 1.10. So in the first year we'll multiply by, here, let me, I'm going to write up here for a second. In year 0, we have 1,000, and then the next year we have 1,000 times 1.10, and then the next year we have 1,000 times 1.10 times 1.10, and so on and so forth. Now, I don't want to, rest of the zero should show up in a second. I don't want to keep writing out 1.10s all day. So for the next one, I'm just going to write repeated multiplication. We did this on day one, 1,000 times 1.10 to the power of 3. Like so. Oops. So down here, if it's been x years, I'm going to write 1,000 times 1.10 to the power of x. And that's going to give me that repeated multiplication that I want. So then if I want to know what's g after 3 years, it's 1,000 times 1.10 cubed, and that turns out to be 1331. And if I want to know how much money I have in the compound account after 10 years, we're definitely going to need a calculator for this one. Don't want to do this by hand. It turns out to be, well, let me grab my calculator. Like I said, I can't do this in my head either. Turns out to be 2,000, whoops, that's not a 2. I don't know if this iPad makes my handwriting better or worse, but well, it's what we have now. $2,593.74. So the downside to exponential functions is we definitely need calculators to find their values. So hopefully you have a calculator that'll allow exponents. But there we go. That's how we would compute an exponential function. And in fact, any exponential function is going to have these 3 parts. It'll have this part, and this part. And that's all it takes to make an exponential function. I'm going to call the 1.1 here the base. I'll call x the exponent. And just like in polynomials, this 1,000 is a constant that's multiplied over on the side. So I'm going to call that coefficient. And so the coefficient tells us where we started. Like here it's 1,000 and we're starting at the point 0, 1,000. And the base tells us how fast that growth is accelerating. So since this is a 1.1, it's only adding 10% every year instead of doubling every so often like the bacteria did. So this is a slower acceleration. Does that make sense?
Yeah.
All right.
Yes.
Sounds good. Good deal. All right. Thank you. Thank you. It's good to get a little bit of feedback from you guys, because otherwise it's like, I don't know. I'm used to scanning your faces every so often in the classroom, and I can't very well do that here, can I? So.
You poor crazy man talking to your computer.
I mean, excuse me. I used to play a lot of multiplayer online games, so this isn't a new experience for me sitting here with a headset on talking to a screen. Just be like, okay, go for the objective, and now it's like, all right, here's what algebra is. It's like, it's not. I've always been a poor crazy man, so here we are.
Do you have Call of Duty?
Never. I've always been really bad at first-person shooters, actually. I don't know why.
No, dude, he plays World of Warcraft, I can tell.
I only played that one for like 5 minutes at a friend's house. Okay, if you want to know, I got way too involved with World of Tanks a few years ago, if you've heard of that one. It's like a first-person shooter, but slower paced. They also did a really good job monetizing it, so don't ask how much I spent. It was terrible. But now I just mostly play little indie games, so. Let's see. Oh yeah, I want to talk about, so we've seen an example of an exponential function here, and I've got the parts labeled, but I just want to talk about how they'll look in general. So let me draw a line here, and we're just going to talk about the anatomy of an exponential function. just like we did with polynomials, I want to see all the variations, all the different shapes that these can take. It turns out there's not very many. They are pretty simple animals. Now, some of the algebra that we'll get into later, especially undoing these things, like if you want to do the steps to undo a function, it's tougher with these than with some other functions, but the basics, the algebra turns out to be pretty simple. So let me take, the general form is going to look like something like f of x equals a times b to the x. And so again, we've got a coefficient, a base, and the exponent's just going to be a variable. Now, this form this is all you need to make an exponential function. Any exponential function takes this shape. Sometimes for applications, you're going to want to apply graph transformations, like you could do a horizontal or vertical stretch or shrink, shift up or down or left or right. And those can have some interesting effects on the graph, but let's talk about the parent function right now. Let's talk about this basic thing here. And just as an example, g of x equals, so I'm going to let the coefficient be 1 here, or yeah, let's let the coefficient be 10. 10 times 2 to the x. This is a very simple example function. It's just going to double every time we move 1 to the right. So if we want to know what the graph looks like, we can plot points. Here's a cool thing about an exponential function, is if I plug in 0, I'm going to get 10 times 2 to the 0. And what's 2 to the 0?
1.
Yes, we're going to have to really be on our toes with those exponent properties. Those are going to be a major feature going forward in this unit. So all those things we learned, like power of 0. If I take a power of -1, I'm dividing. A power of 1/2 is a square root. We have to remember, like, what happens if I add the exponents? What happens if I multiply the exponents? So it might be a good idea between now and next lecture to go back and review the stuff we did, the work we did in 1.1, 1.2, and 1.3, just to make sure you're on your toes for what we're doing next. I know it's probably been 2 weeks since you've thought about algebra, and there's nothing wrong with that. So g of 0 is equal to 10 times 1, which is just 10. And actually, that's always true. That 10 is the same as this 10. So another word for the coefficient is initial value, because whenever I plug in 0, I'm going to just get the coefficient back. The rest of the problem, or the rest of the thing, is going to be a multiplier of 1. So we're just going to see the coefficient. And that works over here as well. If I write f of 0, I'm just going to get a times 1, which is a, because b to the 0 is always 0. So this is the point 0, 10. And then this function, if I plug in g of 1, I'm going to get 10 times 2 to the 1, which is 20. So I'll get 120, and then 240, and 380 would be up there, but I didn't draw the graph that big. So that's the part where it's accelerating upwards. Now, so far we've been doing real-world examples that didn't have a left-hand side, because most of the time we're going to let this x-axis here be time. But just so we have the whole function, we can extend the domain into the negative numbers. If I do g of -1, that's 10 times 2 to the -1. What's 2 to the -1?
1/2.
Perfect. So this is 10 times 1/2, which is 5. So we're going to have, there we go. This will be -1, 5. And if I take g of -2, that's 10 times 2 to the -2, which is 10 times 1/4, which is 2.5. I think you can see a pattern here. We're going 2.5, and then 1 1/4, And then the next one should be, why isn't it coming to me? 5/8, and then 5/16, and so on. It's every time we go to the right, it gets twice as big. So every time we move 1 unit to the left, it's going to be half as tall. So this is -2, 2.5. So that pattern, if every time we go 1 to the right, it doubles, that still works over in the negatives. I went 1 unit to the right, and it doubled from 2.5 to 5. So that works over the whole domain. So this is the shape that any exponential function can have. And like that real world example I showed you before, this is a function where, excuse me, this is a function where, oh yeah, I'm sorry. We have a long tail on the left. It's getting flatter and flatter, but it's never going to quite reach 0. There's nothing I can plug in to make this thing equal to 0. Like if I do -3, it's down to 1.25, and then -4, it's down to 5/8. It's going to keep getting closer and closer to 0, but it's never going to quite reach it. We call that, where it gets closer and closer, we call that an asymptote. I think we might have mentioned these last unit. I don't know how much depth we went into, but these are known as asymptotes. It's a line that the graph approaches but never quite reaches. So let's see. Next thing I want to do with this function is I want to talk about the different properties that it has, like we learned in chapter 3. So the domain of this function, the domain of any exponential function, it's always going to be all real numbers. There's nothing that we're not allowed to plug in. Remember, that's what you're always asking yourself with domain. Is there anything that I cannot plug in here? And with an exponential function, the answer is no. No matter what you put in that exponent, it's legal by the rules of math to evaluate it. Now, the range, on the other hand, not every number can come out of it. Specifically, we're never going to get any negative numbers. Board's frozen again. There we go. We're never going to get any negative numbers, and we can't even get 0. No matter what I plug in for x here, there's never going to be a number that makes, I can't make 2 to the x a 0, and I can't make 2 to the x a negative number. If I plug in like -1,000,000, it's still going to be a tiny bit bigger than 0. And if I plug in +1,000, it's just going to be an astronomically huge number up on the right. But I can never get a negative number, and I can't get 0. So the range is going to be, I'm going to write down here, only positive. And the way I'd write that in an interval form is I'm going to start with parenthesis 0 and go up to infinity. And so that parenthesis is there to say 0 is where it starts, but 0 is not included. I can't get a 0, but I can get any number bigger than 0. So far, so good?
Yes, sir.
Excellent. What other properties do I? Let's see. So there are no x-intercepts. Unless we do a vertical shift, this thing can never cross the x-axis. So that's right out. But we already talked about the initial value. Another word for initial value is that's also the y-intercept. That's not my best penmanship. There we go. This is the y-intercept here. Whatever number is there, if I plug in x equals 0, that's going to be my output. Another thing about this function is, since it's always doubling as we move to the right, it's always getting taller and taller, all the way from the bottom of the range, or the bottom of the domain, to the top of the domain. So this is a function that is always increasing. The one kind of behavior here that might be new to us, because I don't remember how much in depth we went with these last unit, is the end behavior is a little bit different. There's 2 differences I want to talk about with the end behavior. The first thing is that we're going to have to rely on a more intuitive definition. when I told you about end behavior with polynomials, do you remember I said the end behavior is the space way out to the left or way out to the right? And that's still going to be true here, but with polynomials, I said another way is we could say it's further out than any of the roots or turning points. So it's where all of the interesting stuff has already happened and we're just continuing out to the sides. Now, with this function, there's a little problem with that definition, which is that there are no roots and there are no turning points. It never crosses the x-axis and it's always increasing, so there's no roots or turning points to talk of. But when I talk about the end behavior, I just want to define it intuitively as the space way out to the left and way out to the right. And out to the right, it looks very much like a polynomial. I can say as x moves towards infinity, so as we go to the right, f of x is also going to move towards infinity. So as we go to the right, we're going to go up. So this is just like we saw with polynomials. Again, this is that limit arrow notation. What I'm really saying is if I want to go over a certain bar, I just have to go far enough to the right and then I'll make it over that bar. But to the left, we're going to need a slightly new kind of notation. Just a moment. Yes, got it. Okay. Sorry, I had a housefly. All right. So what I've got out to the left is, where'd my pencil go? As x goes towards negative infinity, so as we go to the left, I'm talking about this asymptote here. We're getting closer and closer to the x-axis, but never reaching it. So that can be a useful kind of behavior too. It's almost like we've got two models in one. We've got this exponential growth, where it's getting bigger and bigger in an accelerating way because it's proportional to what we already have. And we've also got out to the left what I'll call exponential decay, which is the further out we go to the left, the flatter it's getting, but it never quite reaches zero. So what I would say with limit arrows is as x goes towards negative infinity, f of x, and this is the perfect case for arrows, it approaches but never reaches zero. So technically what these arrows are saying is no matter how close I want to get to zero, picture setting up a limbo bar just above the x-axis. You can always go far enough to the left that the function's going to limbo under that bar. No matter how low you set the bar, if you go far enough left, it will be able to go under the bar. But paradoxically, it also never is going to reach zero. It just gets lower and lower, slower and slower without ever reaching zero. So that's what this left end behavior is talking about. So it's, like I said, it's like we got two models in one. We've got something that's getting closer and closer but never quite reaching zero, and then we've got something that's just zipping upward very, very fast. As a matter of fact, if you pick any exponential function, doesn't matter which one, literally any exponential function, and then it's going to have a race, and the thing it's racing against is any polynomial. You put them on the same Cartesian plane, eventually the exponential function is going to outrun the polynomial and have higher y values forever. Exponential functions always end up, if you go far enough into the end behavior, being bigger than polynomials, which is kind of a cool property. Excuse me. So these things are growing very fast in the end. Now, this is the kind of exponential function that we'll see the most often. But I want to talk about, there's another kind of exponential function that we won't see as often. So let me take new functions here. F of x equals 2 to the x, and g of x equals 1/2 to the x. So far I've shown you bases of 2, which was really steep, and 1.1, which wasn't very steep. if my base was 1, that would be really boring. If my base was 1, it would be like, okay, 1 to the x. Well, no matter what I plug in for x, the answer is going to be 1, because like 1 times 1 times 1 is 1, and 1 times itself 10 times is 1. It would just be a flat line. So that's the tipping point. If I have a base that's smaller than 1, we get a new kind of behavior. So with 2 to the x, if I plug in a few points, I know if I plug in 0, I'm going to get 1, because 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the 2 is 4. Whereas over here, we said if I plug in a -1, I'm going to get 1/2. And if I plug in a -2, I'm going to get 1/4. So that's because negative exponents flip the fraction. So we get this curve that we've seen a few times today. But watch what happens with 1/2 to the x. I think this is pretty cool. If I plug in 0, anything to the 0 power is 1. So I don't have to worry about that. I know that this is still the point 0, 1. And if I plug in a 1/2 to the first power, I'm going to get 1/2, because anything to the first power is itself. So those are kind of self-explanatory. If I take 1/2 to the 0, I get 1. If I take 1/2 to the 1, I get 1/2. Does anyone remember how to square a fraction?
Square top and bottom.
Thanks. That's exactly what I'm going for. We can square the top and square the bottom and get 1/4. So if I plug in a 2, I'm going to get 1/4 here. And if I plug in a 3, I'll get 1/2 cubed, 1/8. So this is getting flatter and flatter out to the right. But now this is the wild part, is if I plug in a -1, that minus sign is just going to flip the fraction. So instead of being 1/2, it'll be a 2. So if I plug in a -1, I get 2. And if I plug in a -2, first the minus sign flips it, and then the 2 squares it, so we get 4. And as a matter of fact, this whole graph, it's exactly the same shape as the other graph I've drawn on this page. These are literally just horizontal mirrors of each other. If I do a horizontal flip, I go from one to the other. So typically, the way we talk about these, I already used this term once, but I want to write it down now, is we call this exponential growth, and we call this one exponential decay. Not decoy. Whoops. Decay. There we go. Decay. Come on. There we go. Decay. It's weird. Sometimes it updates immediately as I'm writing. Sometimes it takes 5 or 10 seconds. But if that's the worst thing we have to deal with. Nice thing is that none of my apps that I'm chaining together have crashed yet today. So we're already doing better than my last section. So we've got exponential growth and exponential decay here. And when I say it's a horizontal flip, I can prove it to you. If I do a horizontal flip, if I start with f of x equals 2 to the x, if I want to do a horizontal flip on that, I'm going to replace the input, right, f of -x. So I'm going to flip the input around, and that's a horizontal flip. So that'll be 2 to the -x, but I can break up that exponent. -x is the same as -1 times x. And this is one of the places where it comes in handy to remember all of our exponent properties. When I have 2 exponents multiplied together, it's the same as if I take those exponents one at a time. I call this the nested exponents rule. This is the same as 2 to the -1 to the power of, whoops, not 2, 2 to the -1 to the power of x. So this is nested exponents. I can do the -1 power first, and then the power of x second. And 2 to the -1 is 1/2, so my answer is 1/2 to the x. Not 2. Did it again. 1/2 to the x. Update. There we go. So in other words, this function here and this function here really are horizontal mirrors of each other. If we follow that horizontal mirror rule from last unit, we get from one function to the other. So it's really two of the same, two peas in a pod, exponential growth and exponential decay. So exponential growth is great for things like any kind of population, whether we're talking about the population infected by a virus or a population of bacteria growing or a bank account accruing interest. Any of those are great for exponential growth. Kind of a textbook example of exponential decay is a radioactive element. The way those work is that we don't really know when an individual atom of carbon-14 is going to decay into carbon-12. That's a quantum uncertain event. But what we do know is if I have a gram of carbon-14, that's got a billion atoms in it. And on average, they'll decay at a predictable rate. So I can say after about 5,000 years, about half of the carbon will be gone. And so after 10,000 years, 3/4 of the carbon will be gone. And after 15,000 years, only 1/8 of the carbon will be left, and so on. So we're having less and less carbon each step, but it's going to be an asymptote. It's going to go towards zero like that limbo bar from before, but it's never quite going to reach it. That's how radioactive elements decay. So even if you have something highly unstable like radon, you know radon. Oh, I just realized we don't have basements in Georgia usually, do we? We don't have a lot of basements in houses, so I'm from Iowa, and in Iowa, pretty much every house has a basement. And the problem is that the soil in Iowa has a lot of this radioactive gas called radon in it. And so it will leach into your basement over time. It's heavier than air, so it settles in the bottom. And it's really bad for you if you breathe it in. So we have to have little fans in our basements that pump the radon out if we've got a house that's in the kind of soil that has radon in it. Radon has a half-life of 4 days, which is to say that if I have 100 grams of radon now, I'm going to have 50 grams of radon in 4 days. And then in 8 days, that's going to cut in half again to 25. And then 12.5, and then 6.25, and so on. It's never going to be completely gone, but it's shrinking, just like this exponential decay function right here. So exponential decay is great for radioactive elements, and that's going to account for a lot of our examples as we're going into the future with these. But it's nice. So like I said, it's like we have two models in one. We've got exponential functions where the base is less than 1, and exponential functions where the base is bigger than 1. We're never going to let the base be negative because you get really unfriendly behavior. Like a negative number to the power of 1/2 is a complex number, and that's not okay. But a negative number to the power of 1/3 is real again. And then a 4th is complex and a 5th is real. So you get really, really nasty behavior. And we don't want to try to deal with that. Actually, as long as I'm on the iPad, I might as well just show you. Desmos. I don't know why I didn't think of this before. If I do 2 to the power of x, I get this nice behavior. And if I do a horizontal flip and make that a negative x, then, well, we just get that 1/2 to the x. So that's good behavior. And if I do something like 0.8 to the power of x, whoops, that's not what I wanted. 0.8 to the power of x here. So we've got an exponential decay function now. So if that number is bigger than 1, if the base is bigger than 1, we've got growth. If it's less than 1, we've got decay. What I don't want to do is put a negative number down there. So if I did something like -2 to the power of, whoops, not to the power of 2, to the power of x. Let's see if it'll even render this. No, Desmos isn't even going to play with me. I thought Desmos would play with me. I'm sorry. If you can get it to graph one of these, it gets really bad really fast, but I don't remember the trick to make Desmos actually try to render it. It looks bad though. That's a shame.
I think you have to put y equals and then it'll do it.
Let's try it. Please. Nope. It looks like Desmos isn't going to play ball. That's a shame. Maybe if I zoom in a lot. Nope. Oh well. Not everything goes as planned. It's if you can find a program that'll at least try to graph it, it's a shockingly ugly function. So we're not going to try to deal with those. What I do want to do now is let's see. So if we're doing a real world example, so we're going to be modeling. A lot of this chapter is modeling, which is to say it's taking a real world problem and trying to understand how exponential functions can help us do predictions with it. So let's see, for example, I don't know off the top of my head, US population. 329 million. So the US population is 329 million. And populations of people or animals or cells, it's all the same. If I have 100 people in my city and they're having kids every year, it's not going as fast as if I have 1 million people in my city and they're having kids every year. The number of kids you get is proportional to the number of parents you started with. Does that make sense? So even if the birth rate is exactly the same, if I have just one couple, they're going to have maybe 2 or 3 kids and be done. But if I have 100 couples, they'll have 200 or 300 kids before they're done. So population is proportional to what you already have. It turns out that the US population grows at almost exactly 1% per year, which is to say every year it's 1% bigger than the previous year. That's if you balance the birth rate with the death rate, with the immigration rate, it all balances out at we're growing at about 1% per year. So I could ask a question like, what will the population be in the year 2040? And I would use an exponential function to model it. The thing with mathematicians is when we see a problem like this, we try to generalize. Generalizing is a really big part of mathematics, which is to say, if you ask me, given this information, what's the population of the country in 2040? It's not very satisfying for me to say, all right, I'll just add 1%, and then I'll hit enter on my calculator 20 times to go from now until 2040, and there's your answer. And if you ask me, what's the population in 2060, I have to press the button more. I don't like that as much as if I'm able to say, look, here's a formula, no matter what year you want, just plug in that year and it'll give you the answer. I like to have a general solution, which is to say, instead of just solving this problem in front of me now, I want to solve every problem like it. And that's what functions are really good at. They're good at solving every problem like a problem. So what we're going to do is, I'm going to make an exponential function. We call this an exponential model. And that's going to look something like f of x equals a times b to the x. And I just want to pick appropriate numbers for a and b to make this all work. Now, the important thing here is that a is still our initial value. So I'm going to say time 0 is this year. So I'm going to say my initial value is in 2020, in 2020, I'll let x equal 0. and y equal 329. I'm just going to say 329 instead of 329 million. We'll tack the million on at the end. We're allowed to do that. So what that means is I can set my initial value. It's whatever the y-intercept is, and in this case, it's 329. So A is our initial value. B is going to represent growth. And just like in that bank account example, when we were adding 10% interest every year, I was multiplying by 1.10, 1 for what we already had, and the 0.10 for the interest. So here I'm going to let B equal 1.01. That's a 1. So what I'll do next year is I'll multiply by 1.01. So this 1 will represent the 329 million that we already have. And this 0.01 will represent new growth. And so my function is just going to be f of x equals 329 times 1.01 to the x. And that'll be a function that base is just a tiny bit bigger than 1, so we're expecting a pretty flat exponential curve. It's going to be accelerating very slowly at least. But then if I want to know what's the population in 2040, that's 20 years from now. So I would write f of 20 years from now. It's 329 times 1.01 to the power of 20. Definitely need a calculator for that. And if the birth rate and the death rate and the immigration rate stay about the same, looks like we're going to have about 401 million people in the year 2040. So that should be right around when we cross that 400 million people threshold. Does that make sense?
Here.
Excellent. Now, there's so far so good. We've got our solution to this problem. I'll draw a little box. There's our solution. I'm not quite ready to give up this example yet because I want to show you where we're going next. There's something that we don't know how to do. If I ask something like, when will the population equal 500 million? This is a question that we're going to need some new machinery to answer, because we found 400 million just by chance. We could guess and check. Maybe it'll be 19 years to get exactly 400 million. So 500 million, maybe I'd guess 30 years or 35 years and see if I'm over or under, but guess and check is not a satisfactory answer to an algebra problem. We want to come up with a set of steps we can follow and always get the answer. That's our goal in this class, is to be able to do something more sophisticated than guess or check. Not because guess and check is always bad, but because we never know how long it's going to take until we're done. That's the problem with guess and check, is you could be at it for a long, long time. So if I want to know when the population of the country will be 500 million, I could say, well, that's the y value. Whoops, don't want my doc here. The y value is 500 million. And that's going to equal f of some input. That's going to equal 329 times 1.01 to the x. And now I can divide both sides by 329. And I can write 500 over 329 equals 1.01 to the x. But at this point, I'm stuck. I'm completely stuck because x right here is stuck exponent. We can't divide by x, we can't subtract x. None of those operations will get it out of an exponent. Even if I took the whole thing to the x root, I would just have x stuck in an exponent on the other side. So we need a way to undo exponents. And the answer to that is going to be a new kind of function called a logarithm. but that's something that we'll be studying next class. We're not going to talk about those yet today, but that's going to let us finish this problem. So we'll come back to this probably next class and maybe the class after that. It depends how long it takes us to introduce logarithms. And that's going to let us solve problems like this. But what we were able to do is predict what the population will be in any given year. And that's enough to let us guess and check the second half if we want. Does anyone have any questions about this problem? No? All right. I want to do one more example with you today of another thing we can model with exponential functions, and then we'll head off for now. Let's say that we have a science fair project that's due soon. And I know that 5 hours ago, I had an agar plate with a colony of bacteria, and I counted in the microscope, there were 1,000 cells. And I know that now, I counted again in the microscope, and there were 1,800 cells. Now, the science fair is in 14 hours. Whoops. And I don't know how many cells there's going to be. I need to know, so I can put it on my poster, how many cells to expect in 14 hours. So this is a problem we can solve with exponential functions. A cool thing about exponential functions, by the way, is that they're very simple models. So I want to come over here, and this is a side topic, this is a tangent, but I want to talk a tiny bit about degrees of freedom. Do you remember in the problem solving, when I was telling you how our steps for trying to solve a new story problem, I said that you probably want to have as many equations as you have unknown variables? I was like, if you have 2 unknowns, it might be good to have 2 equations. 3 unknowns, we probably need 3 equations. A related concept is degrees of freedom. The degrees of freedom are how many unknowns you have, and you need that many equations to pin them down. So like with a linear function, it's just y equals mx plus b. And there's two parameters here. There's m and b. And to completely determine what linear function I'm talking about, I just need to be able to tell you what m is and what b is. If I've told you the slope and the y-intercept, I've completely determined the equation. So there's 2 degrees of freedom. And that's why if I give you 2 points, you're able to tell me which line goes through them. Any 2 points I pick, there's only 1 line that goes through them. So that's a solvable problem. Whereas with a parabola, I have y equals ax squared plus bx plus c. So to completely decide which quadratic function I'm talking about, I have these 3 parameters. So if I were trying to find a parabola, I would need to give 3 points before we can narrow it down to a specific curve that goes through them. Well, the neat thing with an exponential function is that it's 2 degrees again. It's y equals a times b to the x. So as long as we know a and b, we know everything there is to know about the exponential function. And what that means here is that since we've got 2 data points, that should be enough to solve this equation completely. Does that make sense? I know that's a little bit theoretical, but what it means is we've got these 2 unknowns, a and b. And so since we know the count of cells at 2 different points, in other words, if I can pin that down, whoops, don't want that. If I can pin that down, I have just 2 different points in the plane. There's only ever one exponential function that goes through both. So, let's go ahead and try to solve this. Just as a convention, I'm going to say now is t equals 0. So 14 hours from now will be t equals 14. And to follow that convention, 5 hours ago should be t equals -5. So I'll let t be time in hours. That's my choice. If I wanted to, I could let t be time in minutes, but the numbers would be uglier. So we get to pick. it's our model. We get to pick what we want to do with it. So I want to write a model y equals a times b to the t. Now, one of these two numbers I can already determine. Since a is my initial value, I'm going to say a is equal to 1800. There are 1800 cells right now, so that must be our initial value. So one parameter down, one parameter to go. We've just used the initial value, so now we need to use that 5 hours ago value. Well, so what I'll do is say 5 hours ago, when t is -5, y has to be 1000. So I'll plug that into my model and solve for b. I'll write that 5 hours ago, y was 1000. 1000 equals a times b to the -5. And I know that a was 1800 times b to the -5. Now, if I want to solve for b, I need to divide by 1800. And to finish off this problem, I need to get rid of that exponent of a -5. I'm going to take both sides to a power of -1/5 to cancel it out. And then I just plug that into my calculator. It turns out to be about the same as 1.24. As a matter of fact, I'm going to give a couple more digits. Oops, that's not correct. Calculator says it's about 1.12475. When I'm finding the base of an exponent, I usually want to give a lot of decimal places, because otherwise rounding error gets really bad when you take it to a high power. So payoff is now we know that A is 1800 and B is 1.12475. So I can write y equals 1800 times 1.12475. Question? Go ahead.
I thought we needed logarithms to get
That's a good question. Yes. Thank you for asking. Yes. Here's the difference. If I have like 3 equals 4 to the x, x is stuck in the exponent, I need a log. But if I have 3 equals x to the 4th, I don't need a log because x is in the base.
Okay, that makes sense.
Yep. So then I can write 3 to the 1/4 equals x, and we've solved. Yep. Thank you for asking. That's a very good point. So down here, b was in the base, so I could just undo it by taking the opposite of that exponent, and then they cancel out on the right-hand side. Well, looks like we've got a minute left. Let me just finish off this example real quick. If I want to know how many cells I'll have at my science fair, I plug in 14. Definitely going to need a calculator for this one. It turns out to be approximately 9,333 cells. And then if I wanted to know how many I'll have in 15 or 16 hours, I already have the function, so I can just plug those numbers in as well. But that's how we solve problems with an exponential model. So next class, we'll talk a little bit more about exponential decay and introduce logarithms. Does anyone have any questions?
No, I'm good.
All right. Well, thank you all so much for coming. Like I said, just let me know if you have any trouble. I'm very happy to work with you during all of this crap. The virus and everything. I'm happy to work with you, whatever you need. So I'll be sending you a doodle poll soon for office hours. Question?
Our last test that we took, when will we receive that grade?
So I forgot to grade that. So I'm gonna put that online. Hopefully this weekend.
Okay, sounds good.
I apologize.
You're good.
All right. Any other questions? No. All right. Well, thank you all so much for coming. I will see you again on Wednesday. And like I said, be looking out for that doodle poll, and I'll be putting this lecture and these notes online. And I will see you all next class.